Hello everyone, in this video I will discuss about AC/DC rectifier, single phase, full wave, uncontrolled rectifier. Okay, there are two types of single phase full wave rectifier. First is center tap and second is bridge rectifier. So in this video we will discuss about center tap transformer rectifier. Okay, this is center tap. This is transformer. Okay, this transformer we can see that at the secondary side, tap at the center. Okay, tap at the center. Okay, secondary side. So the voltage will be half compared to the previous one. So there are two voltage here and here, half of the primary voltage. We will analyze the waveform. We will split into two sections. First section is from 0 to pi, and second section is from pi to 2 pi. Okay, two section and okay. During first section, from 0 to pi. Alright, let me delete first. Okay, first section from 0 to pi. Okay, here is a positive cycle. So will be like this: input power input positive. So current will flow from positive terminal. We call it IS, source current. Go here. Then this transformer will transform from primary to secondary. So primary, secondary. Secondary side we have two voltage. First is VS1 and second is VS2. Right? Okay, during positive cycle, current will flow from here to D1. Okay, arrow of current like this, and arrow of diode also same arrow. So that means this diode will be forward bias. And forward bias, short circuit. Okay, short circuit here. Okay, then current is allowed to flow. Current will flow through the D1 and then go until this junction. Current split into two, turn right or go down. However, this current and this diode opposite. So means that diode 2 will be reverse bias, open circuit. Okay, so there is no current here. This side will be open circuit. So all the current will flow from here. All the current flow from here and then go past to the diode as the resistor and go back to VS1. Okay, complete one cycle. Okay, we can see this is output will be the positive terminal at the current enter. Okay, will be polarity will be this. Alright. So we can see from 0 to pi, output positive. Exactly same as the input. Okay, V out equal to, if we do KVL, V out equal to Vs minus Vd1. Okay, in this case, Vd1 equal to 0 due to forward bias, short circuit. So equal V out equal to Vs equal to Vm sine omega t. Okay, this waveform is Vm sine omega t. So that means the output is exactly same as the input. Input waveform like this. So the output will be same as the input waveform from 0 to pi. Okay, how about VD1? We know that VD1 is forward bias by short circuit. So for short circuit, it will 0 volt. Short circuit. Okay, 0 volt. Okay, how about VD2? Okay, to find VD2, we can use KVL. Okay, KVL. Let me change the color. Okay, VD2. VD2 is here. Okay, using KVL here. Right, VD2 equal to VS2, sorry, minus VS2 minus VS1 minus VD1. Okay, VD1 is equal to 0 due to short circuit. So we can finally VS1 and VS2 is equal to minus minus 2 Vm sine omega t. So we can see that V at diode number 2 is equal to twice of Vm. Okay, this one. Okay, this one also we call as PIV, peak inverse voltage of the diode. Okay, next is I naught. I naught is here. Okay, I naught V naught. So that means I naught is equal to V naught over R. Okay, just follow the arrow of same waveform of V out. Okay, then is ID1. ID1 is here. D1. So ID1 here. ID1 is exactly same as I naught. So ID1 follow I naught, same as I naught. From 0 to pi. How about ID2? ID2 is open circuit. Open circuit. So open circuit, there is no current flow. ID2 equal to 0. 0 ampere. From 0 to pi. Okay, next IS. IS is okay here. IS same as the input. Same waveform as the input. So just follow the input waveform. From 0 to pi. Follow the input waveform. Okay, that one is during post 0 to pi angle. Waveform. Next is during second section. Second section is from pi to 2 pi. Okay, that erase. Okay, second section is from pi to 2 pi. From pi to 2 pi, this section is negative cycle. So our input will be negative. So the waveform follow negative. Current will go here, then go to the first coil. So this transformer will transform this voltage to this secondary voltage. Current will flow. Okay, current here in, current will out like this. Okay, this, look at this arrow, I arrow. same as diode arrow, so that means D2 will be forward bias. D2 forward bias, so short circuit. So current will flow, current will allow to flow through diode and go until this junction, split into two, this part and this part. However, D1 is arrow like this, diode the current opposite. So that means this D2 will be reverse bias, open circuit. D1 reverse bias, open circuit. Okay, there is no current flow. So this current cannot flow. All the current will flow here, pass to R1, R resistor, and then go back to S2. So complete one cycle. Waveform will be opposite of the flow of current, opposite waveform. Alright, so we can, so what is V out? Equal to Vs minus Vd2. D2 is 0 due to short circuit. So V0 equal to Vs equal to Vm sine omega t. Okay, you can see that our input is negative cycle, output is positive cycle, positive waveform, sorry. Input negative waveform, output positive waveform. Input is negative, so output positive. Okay, previously during positive cycle, input positive, output also positive. Okay, this is positive. This is the contribute by polarization of D1 and D2. Alright. In terms of diode voltage D1, we know that D1 is reverse bias, open circuit. So to find the voltage across the D1, we can use KVL, outside KVL. Okay, this one VS1. Oh, sorry, VS1. That is VS2. So we have VD1 equal to minus VS1 minus VS2 minus VD2. VD2 is 0 due to short circuit, so equal to minus VS1 minus VS2 equal to minus 2 Vm. Alright, so it means that twice of the input like this, output will be twice. Sorry, not output, the voltage across diode, twice of the Vm. Okay, next is VD1 is, sorry, VD2. Okay, VD2 is diode across, voltage across diode 2. We know that diode 2 is short circuit, so short circuit is 0 volt. Short circuit. Okay, I0. Okay, I0 here is voltage like this, so I0 like this. It will follow same as the voltage, output voltage waveform. Okay, output voltage like this. So I0 also like this, positive cycle. Follow output voltage waveform. ID1 is here, D1 is here, D1 is open circuit. So for open circuit, I will be equal to 0. ID2 ID2 is here. ID2, same circuit between same circuit with I0. So that means ID2 is equal to I0. ID2 equal to I0. Same waveform from pi to pi. How about IS? IS now is negative. IS is negative waveform, so follow the input voltage waveform negative from pi to pi. Right. So next is we derive the equation. So first we use. So the equation for AC/DC rectifier for center tap transformer. Okay, output is, where is output? Output. Okay, here output. Okay, first V out average. Sometimes we call it DC current, DC voltage is equal to area over period. So in this case, we have this area. Period is 0 to pi. So 1 over pi integration from 0 to pi Vm sine omega t d omega t. So we get is 1 over pi Vm okay. This is our V average. Two Vm over pi R average is equal to V over R. So V average over R, 2 Vm over pi R. Okay. Next is PIV. P input voltage is here, 2 Vm. Next is Vrms equal to V peak okay. I think that's all for equation, for derivation of equation. Okay. Okay. We have you can see a center tap transformer. Okay, in this rectifier they need transformer. So this transformer, we know that transformer is expensive. So the disadvantage of this transformer is highly cost and also bulky. However, the advantage of full wave rectifier compared to half wave rectifier is, for full wave rectifier, both waveform, both cycle will be convert. Positive convert to positive, and then the negative cycle convert to positive. However, in single wave, in half wave, the output just convert the one wave only, half of the wave only. In full wave, both waves will convert. This is the, so it means that this mean that this kind of rectifier is more efficient compared to half wave rectifier. Okay, that's all. Thank you. Bye.